Hi, I'm Devi, and today we're going to talk about how to figure out common patterns that you might see in math and sequences. How to determine what kind of pattern a sequence is following. We'll talk about three main kinds of patterns that you're likely to need to know about, and how each of them works, and how you can write recursive formulas for each of those patterns. There's more you can say about each of them. You can find formulas for the sums of the first n terms of a sequence following one of these types, or formulas that don't depend on the previous terms, but just let you plug in n and find out what the nth term is going to be. But for this video, we'll just focus on finding recursive formulas for the patterns. Okay, so first of all, what do I mean by a pattern? I just mean some sequence of numbers. For this video, we'll just talk about positive integers, some sequence of positive integers where there's some kind of regularity to how they're advancing. And for the purposes of this video, I'll assume that the regularity is going to be something pretty simple. So the simplest kind of pattern you might see is something like 1, 4, 7, 10, 13, and so on. Now, hopefully you see that the pattern here is given by adding 3 to the previous number at each step. Now, how could we write a formula for the sequence, a recursive formula, meaning a formula that lets us plug in one element of the sequence and get the next element? Well, let's write it like this. Next equals, and then we want to do something to now, right? So next is what the next element of the sequence is, and now is going to represent the current element of the sequence. Well, if we know now, if now is 7, how do we get next? Well, every time we go up 1 in the sequence, every time we move 1 to the right, we add 3 to the element of the sequence, right? We see 1 plus 3 is 4, 4 plus 3 is 7, and so on. So for this sequence, we have next equals now plus 3. Another way to write this formula, depending on what notation your teacher would like you to use, would be a n plus 1 equals a n plus 3, where a n plus 1 denotes the n plus first member of the sequence, and a n denotes the nth member. A is arbitrary, but it is a standard notation to let some letter refer to the sequence. In this case, we're picking A to refer to the sequence, and then say, okay, let's let A with a subscript denote a particular number of the sequence. So in this case, we'd let 1 be A subscript 1, 4 we'd represent by A subscript 2, 7 by A subscript 3, and so on. This is a standard way to denote sequences. Call them A or some other letter, and let the kth number of the sequence be A sub k. You can use any letter you want, or even some non-standard notation, as long as you specify what it means, but the standard notation is to use a letter near the beginning of the alphabet to denote the sequence as a whole, and then use subscripts to denote the specific elements. It's also common to let the subscript 0 refer to the first element rather than 1. In computer science, if you ever take a computer science course, you'll learn that it's often more common to start counting things with 0 than with 1. Even though in math and in everyday life, it's usually more common to start counting with 1. For the purposes of denoting sequences, you can really use either convention. You can either say 1 is A0, 4 is A1, 7 is A2, or you can say that they're A1, A2, and A3, as we've written here. As long as you're clear about what notation you're using, it doesn't matter. And in fact, for the purpose of finding the recursive equation here, it doesn't matter which notation we use, because the recursive equation is the same over time. It doesn't change, right? Whatever indices individual points in the sequence have, where by the indices, I mean the little subscript numbers that we're using to denote them, it's still the case that if we want to get the n plus first number in the sequence, whatever n is, the number in the sequence that's 1 past n, then we take the number of the sequence that's at n, which is going to be a sub n, and add 3 to it. Any sequence with this pattern is called an arithmetic sequence, where arithmetic is spelled like arithmetic but pronounced arithmetic because it's an adjective. one of the sequences in the original question is in fact an arithmetic sequence, but I'll leave it to you to figure out which one that is. If the difference is something other than 3, then the next now rule or the recursive rule, which you can either write with next now or with the subscript notation, is going to look slightly different, but it would be the same idea with 3 replaced with whatever the repeating difference actually is. So this is what arithmetic sequences look like. An arithmetic sequence is just a sequence where the difference between 2 successive terms is the same. You're always adding the same thing to go from one term to the next, and the recursive formula is always going to look like this. The n plus first term, whatever your notation is for that, is the nth term plus that constant thing. Okay. Another kind of sequence you'll see works just like an arithmetic sequence, except instead of adding the same thing to each term to get the next term, you multiply by the same thing. This kind of sequence is called a geometric sequence. Now, why are the names as they are? Well, I'm not sure there's a great explanation. There are probably reasons for it, but essentially in geometry, it's really common to scale things, right? You might have a drawing, and then whenever you zoom in on a picture, right, what you're doing is essentially you're taking the lengths in the horizontal direction and the vertical direction, the lengths in every direction, in fact, in the picture, and you're multiplying them all by the same thing. If you make a picture twice as big, what you're doing is making everything twice as far apart horizontally and twice as far apart vertically. So you're multiplying everything by something. In a sense, then multiplication is a fundamental thing you do in geometry, whereas in arithmetic, I don't know, I guess addition's more basic. I don't actually know the etymology. That's an interesting question, but it probably has something to do with geometry, I would guess. Anyway, let's see an example for geometric sequence, also called a geometric progression, and an arithmetic sequence, by the way, is also called an arithmetic progression. So let's have one that starts with 1 and 4 again, just to see how it would proceed differently. So if you start with 1 and 4, if it were arithmetic, it would have to proceed as before, because there's only one way to have an arithmetic sequence once you list 2 numbers of it, right? Then you've already determined what that common difference is, as it's called, that you have to add every time. But if this is geometric, now it's going to proceed differently. Instead of adding 3 to get each successive element, now we're going to multiply by 4, which is the ratio between 1 and 4. So we get 1, 4, 16, 64, 256, and so on. Okay, yeah, I think, yeah, there we go, sorry. Okay, that was a stray mark that appeared on my end. That's something with Wyzant. Okay, so this is an example of a geometric progression because we have a common ratio between any pair of terms. So how do we get a next now rule for this? Well, it's really going to work the same way as for an arithmetic progression because the structure is exactly the same, except we've replaced the operation of addition with the operation of multiplication. So instead of having next equals now plus something, for a geometric progression, the next now rule looks like next equals now times something. But not times 3 in this case. In this case, it's actually times 4. We could just as well have a geometric progression where the common ratio, as it's called, is 3, but in this case, it happens to be 4. If we're using sequence notation, then similarly to the arithmetic case, we'd write an plus 1 equals an times, there we go, times 4. So we see the rules for the recursive rules for an arithmetic and geometric sequence are very similar, but surprisingly, if you try to study more questions about them, like how to write formulas for each successive term, how to write formulas for the sums of the first n terms of the sequence as a function of n, and things like that, you'll get different behavior. But there are nice ways to analyze both of them. But for the recursive rules, the structure is very much the same for both of them. And again, just like there was one arithmetic sequence presented in the original question, I'll say that there's also one geometric sequence. But I won't say which it is, since after presenting the 3 types of sequences, I'll hopefully be able to help you figure out on your own which sequence falls into which category. The final kind of sequence I want to discuss is, well, I guess if you want the general name, let me see, I think it's called a Lucas sequence, if I remember correctly. That's what you don't need to know this term for sure, but I think that is the general term for this kind of sequence. Lucas. Arithmetic, geometric, and Lucas. One of these things is not like the other, right? Okay, why is it called that? Well, I assume it's after somebody named Lucas. Anyway, what is a Lucas sequence? Well, a Lucas sequence is something that looks like this. I'll try to give the simplest possible example, which is a standard example called the Fibonacci sequence. 0, 1, 1, 2, 3, 5, 8, 13, and so on. Now, if you haven't seen the sequence before, it might take longer than it did for the last two sequences for you to figure out what's going on here. Well, let's see, what are we adding? 0 plus 1 is 1, 1 plus 1 is 1, 1 plus, or no, sorry, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13. Okay, we're adding different things every time. What about multiplying? 0 times nothing is 1, 1 times 1 is 1, 1 times 2 is 2, 2 times some fraction is 3, 3 halves that is, so okay, nothing nice, but let's listen to what we said when we are looking at what the differences were again. We're adding 1 to get from 0 to 1, 0 to get from 1 to 1, then 1 to get from 1 to 2, 1 again to get from 2 to 3, 2 to get from 3 to 5, and then 5 to get from, or 3 to get from 5 to 8. So what we're actually doing at each step is adding something that we had 2 steps ago. More precisely, to be precise about this, let's write down what we just said. Let's write down the differences. We'll start here. So 1 plus 0 gives you 1, right? Plus 0. 1 plus 1 gives you 2. 2 plus 1 gives you 3. 3 plus 2 gives you 5. 5 plus 3 gives you 8. And 8 plus 5 gives you 13. So if you look at this, what you'll realize is that each step, the thing we have to add is the thing right before that step, not the thing at the current step, but the thing in the sequence right before that. To get from 3 to 5, we don't add 3, but we add 2, because 2 came right before 3. To get from 8 to 13, we don't add 8, but we add 5, because 5 came right before 8. So what that means is that next is now plus what? Well, not plus a constant, not like plus 3 for an arithmetic sequence. With an arithmetic sequence, we're always adding the same thing. Here, what we're adding is the thing that we had before now. So we can write that as previous, or prev. Next is now plus the previous. That applies in every case, right? At the very beginning of the sequence, that's not going to apply because there is no previous. Okay, but after the very beginning, this becomes the rule that the sequence follows. To get 2 as the next from the now 1, we add the previous, which is also 1. To get 1 as the next from 1 being the now, we add the previous, which is 0, the very first member of the sequence. So next equals now plus previous is the rule for the sequence. It's a little different from the next now rules we had before, because here, the value of the next element of the sequence depended only on the current element. We didn't have to look at any previous elements before the current element. Similarly for a geometric sequence. But for a Lucas sequence, we have to look not just at the current element in order to find out what the next element of the sequence is, but we also have to look at the one right before it. We have to look at 2 things, where we are now and where we just were. And only using both those things, adding them together, are we able to find the next thing. How would we write this using sequence notation? Well, as before, an plus 1 can denote next, and now can be denoted by an, right? An is an arbitrary member of the sequence. The next element then, if an is the nth element, so relative to an, the next element is an plus 1. And what is the previous element, if we're considering an to be the current element? Well, it is the element, if an is the current element, it's the nth element, so the previous element is the n minus first element, right? Which is a sub n minus 1. So this is what the recursive formula for a Lucas sequence looks like. an plus 1 equals an plus an minus 1. You could also write it as like an equals an minus 1 plus an minus 2. That would be all right too. You're just basically describing now with a different index. It doesn't matter if you call now the nth element or the n minus first element. There are various ways of describing the sequence. But the key idea is that whatever notation you use for the sequence and whatever notation you use for the recursive rule, you want to express that the n plus first, that any element of the sequence is given as the sum of the two previous elements. Or equivalently, wherever you are at the sequence, in order to get the element after that, so if we started an, say, we want to get the element after that, we want to add the element that was right before where we are now. That's the key thing. Any recursive rule must express that. Now, the interesting thing about a Lucas sequence is that the recursive rule doesn't depend on any particular parameters of the sequence. I gave this one recursive rule, right? For an arithmetic sequence, the recursive rule has this parameter in it, which is the common difference of the sequence, right? Different arithmetic sequences have different common differences. Similarly, different geometric sequences have different common ratios. But all Lucas sequences are going to have the same recursive formula here. And now it may be that Lucas sequence is actually used more generally to allow situations where you can put in coefficients here, meaning you can have rules like this. Maybe your rule for the sequence is bn equals 2 times b, or bn plus 1, I'll say, equals 2 times bn minus bn minus 1. Maybe, I think rules like that actually are also called Lucas sequences. But I'll give a spoiler that the Lucas sequence that we have here in the original problem, remember I said one of the sequences in the original problem is arithmetic, one is geometric, the other one's a Lucas sequence. Its recursive rule is just going to be the simple one without coefficients. An plus 1 is an plus an minus 1, just like this sequence. But think about why that is and think about which sequence it is. Right, it's going to be that simple rule because it's still going to have the structure that you can get the next element always by adding the current element and the previous element. You're not going to have to use coefficients on the elements, but you could have a pattern formed by coefficients of the elements, and then it would have a recursive rule like that. So we talked about 3 typical types of sequences: arithmetic sequences, where you add the same thing at every step; geometric sequences, where you multiply by the same thing at every step; and Lucas sequences, where at every step you look at the 2 previous elements, the current one and the one right before, and you take some combination of them where you multiply them by things and add them together. Typically, you just add them together and that's it. And that's actually what's happening in the problem here. These are the 3 main types of sequences you're likely to encounter. The Lucas type is certainly the most complicated type, and it's hard to identify. But if you know that something's not arithmetic or geometric, which are pretty easy to check, you can check them, in fact, from the first 3 elements. Well, you want to check if the other elements still satisfy it if you think it is arithmetic or geometric from the first 3. But if it's not arithmetic or geometric from the first 3, it's not going to turn arithmetic or geometric later. Because from the first 3, you can already tell, you can already say maybe, hey, the difference isn't constant or the ratio isn't constant, right? So it's pretty easy to check whether a sequence is arithmetic or geometric. If it's not one of those, chances are maybe the pattern you have to identify is a Lucas sequence. And there are various other patterns that exist too. But for a Lucas sequence, this is how you would, this is how you would identify the pattern, simply by trying to find out what you're adding in each step and how the thing that you're adding is related to the previous 2 elements. Try to find some rule that looks something like this, where you get the next element as a simple linear function. And by linear function, I mean just involving addition, multiplication, not involving squares or exponents or anything weird, but something sort of simple like this. If it's a Lucas sequence, then there's a really simple formula like this for next in terms of now and previous. So that's how Lucas sequences work. In practice, you'll probably only ever have this rule: an plus 1 is an plus an minus 1. And you can just look for whether a sequence satisfies that. It probably will if it's a Lucas sequence. You probably won't have to deal with examples that are more complicated than that. So yeah, those are basic types of sequences. If you want to learn about more common patterns, the next one I would suggest looking into is quadratic sequences. I won't go over them here since they don't occur in this problem, but quadratic sequences are where the differences keep increasing steadily. So instead of it being like +3, +3, +3, +3, it'll be like +3, +5, +7, +9. So basically the differences themselves could be an arithmetic sequence, or the differences themselves could be a geometric sequence, or the differences themselves could be a Lucas sequence. You can have endless combinations of sequences. It can be really fun, but these are the basic types to be aware of. Lucas is hardest, but probably if it's a Lucas sequence, it'll just satisfy this simple recursive formula here.